In this video, we will discuss solutions for the multiple choice question part of AP Physics C 2009 examination. The challenge in the examination is to find correct answers within the time assigned in the examination. So this is possible only by a good understanding of concepts of physics and not merely memorizing the equations. So in the discussion, we will clearly illustrate in the examples how application of concepts of physics helps the student to find answers very quickly without having to make any calculations or use any equations. Now we will discuss solutions for the AP Physics C Mechanics multiple choice questions 2009 examination. Now, starting from rest, a vehicle accelerates on a straight level road at the rate of 4 meters per second square for 5 seconds. What is the speed of the vehicle at the end of this time interval? Now the vehicle is moving on a straight level road in one direction, so the velocity and the speed would be the same. Now the acceleration is rate of change of velocity. That means there is an increase of velocity by 4 meters per second in every second. So in 5 seconds the velocity increases by 20 meters per second, and because the vehicle started at rest, from rest, the speed after 5 seconds would be 20 meters per second. This is a case of uniform acceleration. If the vehicle moves with a non-uniform acceleration, in which case the acceleration is a function of time, the acceleration is defined as dv by dt is equal to a of t, then we need to compute the integral to find out the change in velocity, that is the difference in velocity at time t1 and time t2. There is a change in velocity is nothing but integral of at dt, where at is the acceleration which is a function of time. It could be something like that. So but in case of uniform acceleration, then this becomes constant, it becomes a, then the change in velocity is at. That's what we have used in the above problem to find the speed of the vehicle after 5 seconds. So the answer is C. Next question is based on the same data for the same vehicle moving on a straight level road. Now what is the total distance the vehicle travels during this time interval? So in 5 seconds, how much distance it travels? So the distance traveled in a time interval ds is v at t multiplied by dt. That is, suppose if the object is traveling with uniform velocity, then simply the distance traveled is by the velocity or the speed multiplied by the time. But in case it is varying, the velocity is varying with time, which is the case here, that the velocity is varying linearly with time, that is uniform acceleration, then the distance traveled in the time interval is given by the integral vt dt, which is nothing but the area under this line. So using the equation for the velocity, vt is equal to v0 plus ct, that is the equation of this line, then integrate it to find the distance traveled by the vehicle in time t, starting from rest at s0, then we have this integral. So the s0, consider it started from 0 coordinate, then v0 is initial velocity starting from rest is 0. So the distance travelled is given by half at square, where a is 4 and t is 5, so we get 50 meters. So the answer is E. So alternatively, the distance travelled in the case of uniform acceleration is given by the average velocity multiplied by the time. The average velocity is v0 plus vt by 2, that is the velocity at 0 and the velocity at t divided by 2 gives the average velocity, that multiplied by the time gives the distance traveled. It is nothing but the area of the trapezium. So the answer is E. Third question is, all of the following are units of power except. So what is power? Power is the rate of energy, that is energy per unit time. So unit of energy is joule, and per unit time seconds is joules per second is a unit of power. Now watt is nothing but joules per second. Then we have the electron volt, again is a unit of energy, which is energy per second is a unit of power. Newton meters is unit of energy because Newton meters is force into distance. So that is again work done or energy. So Newton meters per second is unit of power. So kilogram meters per second is not the unit of power. So the answer is E. The fourth question is, a dot gun is used to fire two rubber darts with different but unknown masses M1 and M2. The gun exerts the same constant force on each dart, but its magnitude F is unknown. The magnitudes of the accelerations of both the darts A1 and A2 respectively are measured. Which of the following can be determined from this data? Now the F is unknown, but it is the same force is applied on both M1 and M2, giving an acceleration of A1 and A2 respectively. So using Newton's second law, we can write down M1 A1 is equal to M2 A2. So A1 A2 are measured. So we will be able to get the ratio of M1 and A2, M1 and M2, having known A1 and A2. So the answer is C. The fifth question is, an object is thrown vertically upward in a region where G is constant and air resistance is negligible. Its speed is recorded from the moment it leaves the thrower's hand until it reaches its maximum height. Which of the following graphs best represent the object's speed v versus time t? So here we have got two inputs. That is, one is the object is thrown vertically upward, so that it has got some velocity to start with. That is, a t is equal to 0. It has got some velocity. Then it reaches maximum height. So it reaches maximum height. That means it cannot go beyond that. So its velocity is 0 at that point. So we have a situation where the object has initial velocity has some value and the final velocity is 0. So we need to see which of these graphs fulfill this condition. So the first graph has initial 0 velocity, so this cannot be the answer. The second has final velocity is not 0, so this cannot be the answer. Now the third one has initial velocity has got some value and the final velocity is 0. So this fulfill the condition, but let us see whether any other graph satisfies this condition. So now D also initial velocity 0, so this doesn't fulfill the condition. E also initial velocity 0, it doesn't fulfill the condition. So the only graph which fulfills the condition of initial velocity something and final velocity 0 is C. The graph is C. So that is a acceptable answer. So here we have not without using physics, we have taken the basic input that it has to be, the initial velocity has to have some positive value and the final velocity 0. Using this, we have been able to eliminate the wrong answers and got the right answers. But in different situations, we may need to use physics. For example, suppose had there been one more graph which is fulfills the same condition, but with the graph being non-linear and some other shape, then we need to decide which one of the two is going to be the correct answer. From the conditions of the force, we need to decide as to which is the right graph. But in this example, there is no need to use any physics. So this illustrates that one has to use each piece of data to quickly arrive at the answer. The next problem is, an object is if the air resistance is negligible, the speed of a 2 kg sphere that falls from rest through a vertical displacement of 0.2 meter is most nearly. So what we need to find out is the speed of a 2 kg sphere that falls from rest through a vertical displacement of 0.2. So what is the speed it picks up when it falls over a distance of 0.2 meters? So obviously this is falling under the force of gravity. Now the mass of the object does not matter. We know the force of gravity, the acceleration, each body accelerates at the same rate. Here we are taking g is equal to 10 meter per second square. So the mass is not useful in this in solving this problem. And once we know the acceleration due to gravity, so if it accelerates every second 10 meters, the object, and it falls through a displacement of 0.2 meter. Now what is the speed that the sphere will have after traveling 0.2 meters? So we could use this equation that v square t minus v square 0, that is 0 is it is started with from rest, so this is 0. So now we need velocity after time t when it falls through a displacement of 0.2 meters. So once you substitute the values, you get it. It is some simple numerical calculation. So we'll get the answer as B, that is the speed is 2 meter per second. A person holds a portable fire extinguisher that ejects 1 kilogram of water per second horizontally at a speed of 6 meter per second. What horizontal force in newtons must a person exert on the extinguisher in order to prevent it from accelerating? Here this is a case where we have initial system, which is a fire extinguisher, and which is containing water. So once the water moves out, the conservation of momentum, according to Newton's third law, actually the extinguisher also has to move backward if the water moves forward. So in order to prevent that, a force has to be applied. So the forward force is 1 kilogram water per second, and speed of 6 meter per second, the force is 6 Newton. So the person has to apply a force of 6 Newton, so to cancel the backward force by the ejecting water. The eighth problem is a disk is free to rotate about an axis perpendicular to the disk through its center. If the disk starts from rest and accelerates uniformly at the rate of 3 radians per second square for 4 seconds, its angular displacement during this time is. Now this is a problem of kinematics, that is we need to know the relation between motion variables of angular motion. And we know that the relation between motion variables, the kinematic relations, are the same or similar for the angular motion as well as and linear motion. So we use the relation for angular displacement, which is theta t is equal to theta 0 plus omega 0 t plus half alpha t square, where theta is the displacement and omega is the angular velocity and alpha is the angular acceleration, and t is the time during which the displacement has taken place. So we know that theta 0, we can take theta 0 to be 0. Then what we need is theta t minus theta 0, that is the displacement is what we need. So then we get omega 0 is 0 because it is starting from rest. Then alpha is 3 and t is 4. So we get 24 radians. So the answer is D. The 9th and 10th problems. A 2 kilogram mass connected to a spring oscillates on a horizontal frictionless surface with simple harmonic motion of amplitude 0.4 meter. The spring constant is 50 newtons per meter. Now we need to find the period of the motion. The frictionless surface means there is no force of friction acting on the oscillating spring. The spring is oscillating because if it is just if it is stretched and let it go, then it starts oscillating. So the equation of motion which describes the spring motion of the spring is y is equal to a sin omega t, where a is the amplitude, that means we stretch by a. Then omega is given by root k by m. K is the spring constant, which is given to be 50 newtons per meter. M is the mass of the spring, which is 2 kilograms. then the time period is given by 2 pi by w omega, then we get the substituting the values, we get the time period as 0.4 pi seconds. The answer is C. That is 2 pi by 5 is 0.4 pi. The 10th question, the maximum velocity occurs where, see, when the spring is stretched by an amplitude A and let it go, it oscillates with amplitude A, that is, it moves to left by A and right by A. It oscillates between plus A and minus A. And when it is at the extreme positions, that is at A, the velocity is 0, so the kinetic energy is 0, whereas the potential energy is maximum. So the conservation of energy demands that the total energy is constant. So when the spring returns to the equilibrium position, the potential energy is 0 because the displacement is 0. So the entire energy is converted in the form of kinetic energy. So the maximum velocity of the spring is when the displacement from equilibrium is equal to 0. So the answer is E. The 11th question is, a student is asked to determine the mass of Jupiter. Knowing which of the following about Jupiter and one of its motion will allow the determination to be made. So now we need to know how what is the parameter which is affected by the mass of Jupiter. Now the time it takes for Jupiter to orbit the Sun, this is not affected by mass of Jupiter. It is affected by mass of the Sun and the radius in which the Jupiter is moving. So one is not useful to find the mass of Jupiter. The time it takes for the Moon to orbit the Jupiter. So this is affected by the mass of the Jupiter. Now the average distance between the Moon and Jupiter. So the time it takes for the Moon to orbit around Jupiter depends upon the distance, average distance between the Moon and the Jupiter, and the mass of Jupiter, because the mass of Jupiter gives the force, is responsible for the the Moon orbiting the Jupiter. So the mass of the Jupiter can be found by knowing 2 and 3. The time period is a function of the mass and the distance. Okay, so there is an equation. There are 3 variables. If 2 are known, the third can be found. So 2 and 3. So the answer is E. A disc sliding on a horizontal surface that has negligible friction collides with a rod that is free to move and rotate on the surface, as shown in the top view above. Which of the following quantities must be the same for the disc rod system before and after the collision? So here the system consists of the disc and the rod, and there are no external forces and there are no external torques. If there are no external force and external torques, the force is responsible for change in momentum and the torque is responsible for change in angular momentum. So both the linear momentum and angular momentum have to be conserved because there are no external forces or torques. Whereas the kinetic energy, conservation of kinetic energy depends upon the nature of the collision. If it is an elastic collision, it is conserved. If it is inelastic, the kinetic energy is not conserved. So it depends on the situation. So from the given information, we can only say that the linear momentum and angular momentum are conserved. That is 1 and 2. So the answer is C. The 13th question is, the velocity v of an elevator moving upward between adjacent floors is shown as a function of time t in the graph above. At which of the following times is the force exerted by the elevator floor on a passenger the least? So when a person stands in an elevator, the elevator is exerting a force because the person is standing on the elevator. So when the elevator is at rest, the person is at rest. So if we look at the forces acting on the person, for a person to be at rest, the force of gravity and the force exerted by the elevator floor must be the same, because they are the two opposing forces. The reaction force by the elevator floor cancels the downward force of gravity acting on the person. So that keeps the person at rest. So if the elevator is moving up, that means the person is moving up. So for a person to move up, the force exerted by the elevator floor must be greater than the force of gravity acting downwards for making the person move up. So, and when the elevator comes down, then the force of gravity should be more than the reaction force. So for the person to come down or to have an acceleration in the downward direction, for a person to have an acceleration in the downward direction, the force of gravity has to be more than the reaction force exerted by the elevator floor. So in this case, if you look at the graph, the acceleration is positive on the left of the graph, that is till 4 seconds, till 3 seconds, till 4 seconds it is the velocity is increasing. So that means the elevator must be exerting more force than the force of gravity. So the person is elevator moving up, accelerating, and the person also is accelerating. Then after 4 seconds, the velocity of the elevator is falling down, so the velocity of the person is also reducing. That means the acceleration is negative. So the acceleration is negative means the force of the reaction force is less than the force of gravity. So only then the acceleration can be negative. And when the acceleration, when the force exerted by the floor is the least, the acceleration, downward acceleration is maximum. There is a change in velocity or decrease in velocity is maximum when the force exerted by the floor is the least. Okay. So that we can see the change in velocity is maximum. There is a gradient. We have to take the gradient of the curve v versus t. Then we find at t is equal to 6 seconds. T is equal to 6 seconds. We find this is a steep fall in the velocity, indicating that the change in velocity is is maximum here. So that means the force exerted by the elevator is the least. So the gravity is acting more, resulting in maximum acceleration downward at this point of time. So the answer is t is equal to 6 seconds. See, for the acceleration to be upward, the reaction force must be greater than gravity, and for the acceleration to be downward, the reaction force must be less than gravity. So reaction force is the least when downward acceleration is maximum. So, and we know that weightlessness results in case of free fall. So the answer is E. This is a case of an object sliding on an inclined plane. So an object of mass m moves with acceleration a down a frictionless incline that makes an angle with the horizontal as shown above. Now, if n is a normal force exerted by the plane on the block, which of the following is correct? So now n is the normal force. So the n is equal to mg is not correct, because the mg is acting in this direction, and whereas this is a normal force and this is mg. The normal force is balanced only by the vertical the component of the weight which is perpendicular to the inclined plane. So n is not equal to mg, and n is also not equal to ma, because when the object is accelerating along this plane, the force, the normal force is not causing the motion of the object in this direction. The force which is causing the motion in this direction is mg sin theta, which is the horizontal component of the weight. So a is equal to mg sin theta. This is not true, because a is acceleration, whereas mg sin theta is a force. Now a is equal to g sin theta. So this is correct, because this is acceleration g sin theta, because the force is mg sin theta. So the force by mass is g sin theta, which is acceleration. So a is equal to g sin theta. So answer is D. A disk of mass m slides with negligible friction along a flat surface with a velocity v. The disk strikes a wall head-on and bounces back in the opposite direction with a kinetic energy one-fourth of its initial kinetic energy. What is the final velocity of the disk? So that means the disk collides with the wall head-on and it bounces back, and then its kinetic energy is reduced. That means it is an inelastic collision wherein it loses its kinetic energy. Now the kinetic energy is one-fourth. So that means the kinetic energy depends upon the velocity and mass. So the kinetic energy final is one-fourth of the initial kinetic energy. So we know that it is the final velocity will be equal to the initial velocity by 2. But the particle, the disk is moving in the opposite direction. So it must be having the negative sign. So here we are talking about the velocity. The direction is also important. So the answer is minus v by 2. So which is D. The following pairs of equations show how the x and y coordinates of a particular particle vary with time. In the equations A, B, A, comma B and omega are non-zero constants. Choose the pair of equations that best answer each of the following questions. A choice may be used once, more than once, or not at all. That is, in the questions which are given, we can use A, B, C, D once or more than once or not at all. So we have to find out which of these describe the motion given in the following problems. So now, which pair of equations can describe the path of a particle moving with zero acceleration? Zero acceleration means now the equations which are describing, they are describing the motion. So zero acceleration means the second derivative of x and y, because this gives the coordinate of the x coordinate of the moving object, and this is the y coordinate, and if the second differential, because the dx by dt is velocity in the x direction, dy by dt is the velocity in the y direction, whereas the second differential gives the acceleration. So the equations for which the second differentials are zero, that set of equation describes the motion for which the acceleration is zero. So we can see here the second derivative of x and y are zero. So the answer for that question is C. Which pair of equations can describe the path of particle moving with zero acceleration? So we have to find out the second differential, whichever is having zero, that pair of equation describe the path of a particle moving with zero acceleration. Now, which pair of equations can describe the path of a particle moving with an acceleration that is perpendicular to the velocity of the particle at t is equal to 0 and remains constant in magnitude and direction? So we have to find out which equation will have the acceleration perpendicular to the velocity of the particle at t is equal to 0 and constant in magnitude and direction. So let us look at these equations now. Of the two conditions that the pair of equations have to meet, it is simple to verify the condition that the acceleration remains constant in magnitude and direction. So we can check the first pair of equations has this acceleration is omega square a minus xi minus yj. So here x is a displacement and y also is a displacement. So this has constant magnitude and also direction. Now the fifth pair also acceleration has constant magnitude and direction. So the pair of equations which satisfy our conditions will be one of these two pair of equations. So now we have to see whether which of these equations satisfy the other condition, that is acceleration is perpendicular to the velocity at t is equal to 0. So we see here at t is equal to 0 the velocity is 0, so obviously this doesn't satisfy the condition. So the fifth pair at t is equal to 0 the velocity is in the direction of x-axis, that is a of I, and acceleration is in the direction of j, that is the y-axis. So the acceleration is perpendicular to velocity at t is equal to 0. So this pair, the fifth pair, satisfies the condition specified in the problem 17. So the answer is E. So the next question is, which pair of equations can describe the path of a particle that moves with a constant speed and with a non-zero acceleration that is constant in magnitude? So here also we can see first what is the pair of equation which satisfies the condition that the acceleration is constant in magnitude and non-zero. So it can be the fifth pair and the fourth pair, and so this is 0, so this doesn't fit in. So this again is a function of time, so this does not fit in. It doesn't satisfy the condition that the acceleration is constant in magnitude. Now if you look at this, here we are having x which is a the amplitude. So we had the equation x is equal to a cos omega t. So x is a cos omega t and y is a sin omega t. So the magnitude of this is x square plus y square under root. That is, if you have a vector which is x plus y, then xi plus y. So this is like a, we can take the x-axis is x and y is y. So the hypotenuse, the Pythagoras theorem. So x square plus y square is the magnitude, that is the resultant vector. So the magnitude is root x square plus y square. So which is because x is a cos omega t, y is a sin omega t, so x square plus y square is capital A square. So under root is a. So acceleration becomes omega square multiplied by a square. So which is again constant. So now, so we have three pairs which satisfy the condition the acceleration is constant in magnitude. That is the first one, the third one, the fourth one, and the fifth one. But here we see the acceleration and velocity are always parallel. So the perpendicular constraint that acceleration is perpendicular to velocity is not satisfied by this. And here also this satisfies only at t is equal to 0. So these two also do not fulfill the condition that acceleration has to be perpendicular to velocity. So we are only left with this. So this is a answer, that is, the answer is A. So we can verify whether it is true or not that the acceleration is perpendicular to velocity. Here we are having this vector is x minus yi plus xj. Here it is minus xi minus yj. So for the two vectors to be perpendicular to each other, the dot product has to be 0. So we know that this becomes minus y into minus x is xy. So I dot j is 0. So then the other thing is x j dot I is 0. So j dot j is minus. So this is minus xy and the first one was plus xy. So it is 0. So the dot product of the two vectors, the velocity vector and acceleration vector, is 0. So it is verified that the acceleration is perpendicular to velocity. So the 18th problem, the answer is A. Yeah, in this problem, a skier slides at constant speed down a slope, inclined at an angle psi to the horizontal. If air resistance is negligible, the coefficient of friction mu between the skies and the snow is equal to, here air resistance is negligible. That means the only force that is acting, forces that are acting are the component of the gravity along the plane, which is responsible for downward, which can applies the force downward, and the other force is the force of friction, which is upward against the motion. So, if the sky is moving with constant speed, that means the force of friction and the force of gravity, the component of the gravity along the plane are equal. So, for the skies to move with constant speed, so the force of friction is given by the coefficient of friction mu multiplied by the normal force. So, here the normal force is, now the force of gravity acts downwards. That is vertical, and the component of the gravity along the plane is mg sine theta. If m is the mass of the person and g is the acceleration due to gravity, this is mg sine theta, and this is mg sine psi. Okay, here we are having psi, mg sine psi, and the component perpendicular to the plane is mg cos psi. So the normal force has to be mg cos psi, because there is no motion in this direction. So the force of friction is mu mg cos psi, and whereas the force which is acting in this direction is mg sin psi. Both need to be equal for the skies to move with constant speed. So a skyer to move with the constant speed. So mu mg cos psi is equal to mg sin psi. This gives us mu is equal to tan psi. So the answer is E. A 2000 kilogram car initially at rest is accelerated along a horizontal roadway at 3 meter per second square. What is the average power required to bring the car to final speed of 20 meter per second? Here the final speed is 20 meter per second, so the car will have the kinetic energy given by half mv square. Now this energy is achieved by the car. Car will have this energy after some time, during which the car reaches speed of 20 meter per second, accelerating at the rate of 3 meter per second square. So the time that is required for it to reach 20 meter per second is nothing but 20 by 3 seconds. So the power is the average power is the total energy by the total time. So the total energy half mv square gives us this figure. So this is half m is 1000 and into v square is 400. So this is the total energy, so many joules. Then the time is 20 by 3 seconds. The power is the energy by the time. So the answer is 6 into 10 to the power of 4 watts, which is answer E. So in this problem, it is a person raft system. Is a closed system. There are no external forces. So a person is standing at one end of uniform raft of length L that is floating motionless on water, as shown above. The center of mass of the person raft system is distance d from the center of the raft. That is, this is the center of the raft, and the center of mass is here, which is a distance d from the center of mass. Now the person then walks to the other end of the raft. If friction between the raft and the water is negligible, how far does the raft move relative to the water? Now, as the person moves, the raft has to move in the opposite direction to conserve the momentum, because for every action there is an equal and opposite reaction. So this is a closed system. So as the person moves this way, the raft has to move in the opposite direction. Now the distance through which it moves depends upon the conservation of momentum principle. So here we can apply the conservation of momentum principle, and then can find out what is the distance through which the raft moves. Finally, after the raft, here this equation defines the center of mass. Now we are having m is the mass of the person and r is the mass of the raft. So the center of mass is at L by 2 plus d. That is, from the center, suppose if we take the 0 of the coordinate system is on the left. If this is 0, the center of mass is at L by 2 plus d. Center of mass is at L by 2 plus d. So we have the and the person is at a distance L, and the mass of the raft is here L by 2. So we have m into L plus R L by 2 is equal to m plus R L by 2 plus d. So this is the center of mass equation. Now from this we can get the second equation. Then conservation of momentum gives us this: the momentum of the magnitude of the momentum of the person should be equal to the magnitude of the momentum of the raft, but both are in opposite directions. Now when the person moves on the raft, now the raft moves in the opposite direction. So if the person moves for a time t, then because the raft also moves in the opposite direction, so the Vm plus Vr into t is L, because the raft is not stationary. If the raft is stationary, then it is only Vm into t is equal to L, because but the raft is moving in the relative to the person, the raft is moving, so the velocity of the person is Vm plus Vr into t is equal to L. So from this we can simplify, and then we will find that Vrt, that is the distance moved by the raft, is equal to 2d. So this is one way of doing the problem, but it requires some calculation, simplification of some algebraic expressions. But suppose if we apply the concept that, see, in a closed system, the center of mass of an isolated system is stationary. That is actually a consequence of conservation of momentum, is that the center of mass of an isolated system is conserved. Actually, if the system as such, the whole system was moving with some velocity v, the momentum of the system will remain as it is. In case of an isolated system which is at rest, then the center of mass also will be rest. So as a person reaches to the left of the raft, the center of mass shifts to a point d to the left of the center of the raft. That is, as a person moves from this end to this end, now the center of mass will be at this point. That is d from the center towards this. So that is going to be the center of mass. But if the center of mass has to be stationary, then this point should have moved here. That means this point should have moved a distance of 2d. That means the raft should have moved a distance of 2d. So this is a much simpler and faster way of getting the answer. But one needs to know that the implication of conservation of momentum, how it applies to the center of mass, and use that fact to solve the problem. So the object of mass m shown above is dropped from rest near its surface and experiences a resistive force of magnitude kV, where v is the speed of the object and k is constant. Which of the following expressions can be used to find v as a function of time? So here, see, the forces which are acting on the object are the forces which are acting are the force of gravity, and the resistive force, which is given to be k of v, where v is the velocity. Now this force produces acceleration in the object, so that is given by m dv, that is dv by dt is the acceleration. So we write the equation for dv by dt. This is equal to mg minus kv. So this we can write as dv m by mg minus kv, mg minus kv is equal to, what do we get, dt. So integrate on both sides. So this goes from 0 to V and this goes from 0 to T. So this is the equation that we will have. So this is the equation, that is dV by mg minus kV. We had m here, so but that can be brought here. So the answer for this problem is A. Simply we have to write down the Newton's second law, the equation for motion. Then by integrating we can get this expression A. Answer is A. Now this is a problem involving moment of inertia, angular motion. A solid cylinder of mass m and radius r has a string wound around it. A person holding the string pulls it vertically upward as shown above, such that the cylinder is suspended in midair for a brief time, interval delta t, and its center of mass does not move. The tension in the string is T, and the rotational inertia of the cylinder about its axis is half mr square. The net force on the cylinder during the time interval delta T is, here what is happening is the cylinder doesn't move. The cylinder doesn't move. So that means there is no translational motion. There is no translational motion means the force, there is no translational force. So the force of tension cancels with the force of gravity. So T is equal to mg. So that means the net force on the cylinder has to be 0 for the center of mass to be stationary. So the answer is C. Now the next question, the linear acceleration of the person hand during the time interval delta t. See, during this time interval delta t, t is equal to fg. Okay. Now the angular motion is achieved by a torque. And what is the torque? Torque is the force which is applied and the perpendicular distance from the axis of rotation. So this is the axis of rotation, and here is the tension, and this is R. So we know that the tension T, which also is mg during the time interval delta t. So mgr is the torque. So this mgr, the torque, creates acceleration which is equal to the torque mgr is equal to the moment of inertia into angular acceleration alpha. Okay. So I alpha is equal to mgr. Okay. Now I alpha is equal to mgr. I is given to be half mr square. What is alpha? Alpha is related to linear acceleration by a by r. So alpha is a by r. So mg capital R is equal to half mr square multiplied by a by r. That's a capital R. So once you simplify that, we will find that the linear acceleration is equal to 2g, which is the answer is B. Problem 25. A figure skater goes into a spin with arms fully extended. Which of the following describes the changes in the rotational kinetic energy and angular momentum of the skater as the skater's arms are brought towards the body? So in this case, there are no external forces, external torques or forces acting. So when there are no external forces, torques, the angular momentum has to be conserved. So the angular momentum is equal to the moment of inertia and the angular velocity. And if you take L1 is the initial angular momentum, L2 is the final angular momentum. So these two should be equal. Now when the arms are brought towards the body, the moment of inertia decreases because the mass distribution is reduced. See, the moment of inertia is mr square, r is reduced, so I2 is less than I1, so that makes omega 2 greater than omega 1. Now we know that I2 omega 2 is equal to I1 omega 1 because the conservation of angular momentum, because there are no external torques. So then I2 omega 2 square will be greater than I1 omega 1 square because I2 omega 2 is equal to I1 omega 1. Omega 2 is greater than omega 1. So this relation is holds good. So that means the rotational kinetic energy increases, whereas the angular momentum remains the same. So So the answer is the rotational kinetic energy increases and the angular momentum remains the same. So answer is C. Objects 1 and 2 have the same momentum. Object 1 can have more kinetic energy than object 2. If compared to with object 2, it has, see now object 1 and 2 have the same momentum, that means m1 v1 is equal to m2 v2. Object 1 can have more kinetic energy than object 2, that means we want m1 v1 square to be more than m2 v2 square. So that is possible if v1 is greater than v2. That means if it is moving faster, then it will have more kinetic energy than one will have more kinetic energy than object 2. Now the 26th answer is E. Okay. Now a 5 kilogram object is propelled from rest at time t is equal to 0 by a net force F that always acts in the same direction. The magnitude of F in newtons is given as a function of t in seconds by F is equal to 0.5 t. What is the speed of the object at t is equal to 4 seconds? So here we have got the force which is a function of time. So we have to find out the acceleration as a function of time. So F is equal to ma. So a of t is equal to f of t by m. This is 5. So we have at is equal to 0.1 t. So what we want is the acceleration at 4 seconds. So we have to find out v at 4 is equal to v at 0 plus 0 to 4 at dt. So have 0.1 t, integrate it, then we will find the answer is 0.8 meters per second. Two balls with masses m and 2m approach each other with equal speeds v on a horizontal frictionless table as shown in the top view above. Which of the following shows possible velocities of the balls for a time soon after the balls collide? Now here we are having a ball, one ball is moving to the right with momentum mv, then mv, and another ball moving to the left with momentum 2mv. So the total momentum is mb in the to the left. So whatever situation that is in these figures should have the net momentum towards the left of mb. Now this is not possible because it is only along y. This again is not possible because there is a net momentum in the is not along the x-axis. The net momentum is not along the x-axis. Here also it is not along the x-axis. Now here if you see in this case, this is 2m and this is m, but then the momentum vector is longer, So this momentum vector is shorter. So if we see the net momentum, so this will be, if you resolve the momentum here into components in the along the x and along y, so this is likely to give because this has got a smaller angle, so this will have component here, this will have, so they are likely to cancel, and so we will have the net in this direction. So the answer is D. A projectile is launched from a level ground with an initial speed v0 at an angle theta with the horizontal. If air resistance is negligible, how long will the projectile remain in the air? So here, see, when the projectile is launched from a level ground, we will have the situation like this. We are having the projectile is launched at an angle theta, so it will have the vertical component is v0 sin theta and the horizontal component is v0 cos theta. So the time it remains in air is the time it takes for it to go up. The vertical velocity becomes 0. Then in the same time it comes back. So that is the time during which the projectile stays in the air. So the time it takes for it to go to the maximum height is v0 sin theta is equal to gt, that is when the velocity becomes 0. So t is v0 sin theta by g. So the ball remains in the air for a time 2v0, that is double this time, 2v0 sin theta by g. So the answer is E. One end of a string is fixed as an object attached to the other end moves on a horizontal plane with uniform circular motion of radius r and frequency f. The tension in the string is Fs. If both the radius and frequency are doubled, the tension is. So here the tension in the string balances that provides the centripetal force for the object to move. So Fs is equal to mv square by r. So now here the frequency is v by 2 pi r is the frequency, because 2 pi r by v is the time it takes for one circle. One cycle takes 2 pi r by v, so the frequency is v by 2 pi r is f. So yeah, so what we have is Fs. Now substituting for v, we will have m f square r 2 pi square. So now what it says is if both the radius and frequency are doubled, see the frequency is doubled, this becomes 4, radius is doubled, this becomes 2, 4 into 2, so this is 8. So the tension is 8 times Fs. So the answer is E. An object of unknown mass is initially at rest and dropped from a height h. It reaches the ground with a velocity v1. The same object is then raised again to the same height h, but this time is thrown downward with velocity v1. It now reaches the ground with the new velocity v2. How is the v2 related to v1? So here, initially the object is at rest and dropped from height h, it reaches the ground with a velocity v1. So this object which was at height h had a potential energy which is mgh, then it gets a velocity v1, that means the mgh becomes half mv1 square. So that means v1 square is equal to 2gh. Okay. So now the second time the object is dropped with velocity downward with velocity v1. Okay. Now that means to start with, it had a kinetic energy of half mv1 square. To that, it reaches the ground with a new velocity v2. So that half mv1 square plus half mv1 square. That what we get is mv1 square is the energy. mv1 square is the energy. So we will have v2 is equal to root 2 v1. The answer is C. That is, v2 is the new velocity. So mv2 of mv2 square is equal to mv1 square. Okay. Now initial velocity gh mgh is equal to half mv1 square. Now next time it has this energy. It is dropped with velocity v1, so it has this energy. Again the same energy is picked up because there is a fall of mgh, so it picks up same energy. So it will have the energy which is mv1 square. So the kinetic energy, the new velocity, is half mv2 square. So this gives v2 square is equal to 2v1 square. So v2 is root 2v1. So that is how we get the answer C. Three identical disks are initially at rest on a frictionless horizontal table with their edges touching to form a triangle, as shown in the top view above. That's not there. So basically these three will be touching together. With their touching to form a triangle, as shown in the top view above. An explosion occurs within the triangle, propelling the disks horizontally along the surface. Which of the following diagrams shows a possible position of the disks at a later time? In this diagram, the triangle is shown in its original position. Okay, so this is the original position of the triangle. So that means these two disks were here, and because of the explosion they have moved out. Now we know that the explosion should not change the center of mass of the configuration. So what is the thing which doesn't change the configuration? So we can see that how many we are having. Yes, see, now here there is no vertical movement, there is only horizontal movement. Now for the center of mass to remain here, this is a triangle, so center of mass must be somewhere here. So the mass distribution on both sides, the moment should be the same. So here the two disks have moved by this much, so the one disks have to move double for the center of mass to be stationary. So that's how the answer is E. That is, we have to find out, we have to see that the configuration should not alter the center of mass. Now in this case, the original thing, center of mass is there somewhere in between. So obviously in this case the center of mass cannot be there, center of mass will come somewhere here. So this is not the correct thing. So in this case, see here also the center of mass will be somewhere here. So this is not the correct thing, this also is not the correct thing. So this also center of mass will be somewhere here. So in this case we have to see the center of mass, because these are closer to this, the center of mass will shift this side. So in this case, because this has moved more than the two disks here, so the center of mass is likely to be here. So the answer is C. Here the figure above represents satellites S2 and S3 of equal mass orbiting Earth in circles of radius 2RE and 3RE respectively, where RE is the radius of Earth. How does the kinetic energy and the angular momentum of S3 compare with those of S2? Now here the masses of the satellites being the same, S2 and S3. Now the velocity in the orbit which is closer to the Earth, in this set this will have velocity will be more compared to the velocity of the satellite here. So the kinetic energy of the satellite S2 will be more than the kinetic energy of the satellite S3, because the velocity is here more. Because we know the escape velocity varies as 1 over root r. So this will have more velocity. So that means here we can see it is less for S3. Yeah. So one of these two will be the correct answer. Okay. So the kinetic energy is less for S3. What about angular momentum? Now angular momentum is the momentum mv into r. So here we know v varies over 1 over root r, but the radius is over r. So this varies faster than v. So mvr, the angular momentum will be of S3 will be higher than the angular momentum of S2, because v here reduces by only root r, but whereas the radius goes by r. So this will have greater angular momentum. S3 will have greater angular momentum. So the answer is A. The kinetic energy is less for S3 and greater for the angular momentum is greater for S3. Yeah. Here a car is traveling along a straight level road. When it runs out of gas at time t is equal to 0, from this time on the net force on the car is resistive force minus kV, where v is velocity and k is a constant. Which of the following pairs of graphs best represents the speed v and position x of the car as a function of time after t is equal to? So in this problem, a car is traveling along a straight level road. When it runs out of gas at time t is equal to 0, from this time on the net force on the car is a resistive force of minus kV, where v is velocity and k is a constant. Which of the following pairs of graphs best represents the speed v and position x of the car as a function of time after t is equal to 0? First it is simple to look at the graph for x and then decide which one are allowed. So we can see the x, the first graph, the second one are not the ones, because the x is falling down. No, x has to increase, whereas x is falling down. So we can eliminate a and b from the condition that the variation of x shown is not correct. Then rest of them are one of the three is possible. Now the force is proportional to the minus v. So the variation of velocity with time cannot be linear. This is possible only for a constant force only. This is possible. Then we are left with C and D. Now here the force is proportional to minus kV. That means when the velocity is high, the fall is rapid, and as the velocity decreases, the fall is more the rate of fall reduces as the velocity reduces. So that we can see is reflected in the graph D. Initially it falls when the velocity is high, the force is high, so it falls. But as the velocity reduces, the rate of fall also is reduced. So the correct answer is D. We could also write down in this case equation for motion that dv by m dv by dt, or ma is equal to minus kv. Then we can solve the differential equation. Then we will get velocity is exponential minus kt. So from that also one can answer the problem. But even without having to do that calculus, one can qualitatively argue and then arrive at the conclusion that D is the answer. Yeah. Here, a block of mass m is placed against the inner wall of a hollow cylinder of radius r that rotates about a vertical axis with a constant angular velocity w. In order for friction to prevent the mass from sliding down the wall, the coefficient of static friction mu between the mass and the wall must satisfy which of the following inequalities. Now basically the mass m is stuck to the inner wall of the hollow cylinder because of the velocity with which it is rotating. That is, if this is rotating with velocity v, so mv square by r is the force. So that will be the normal force to acting on the mass m. So the force of friction will be mu mv square by r. So the force of static friction mu mv square by r, when it cancels with the gravity force mg, it is a gravity force which will make it fall down. But if the force of static friction is more or equal to the gravitational force mg, then the mass will not fall down. So the force of static friction is mu multiplied with the normal force, which is mv square by r. So v is r omega. So mu into mv square by r should be equal to mg. So we can substitute v is equal to r omega. Then we will find that mu should be greater than or equal to g by w square r for the mass to get stuck in the inner wall of the cylinder and not fall. So the answer is B.